Second kind of modulus that we're going to consider is the shear modulus, and I've written here to remind us again that in general an elastic modulus is defined to be a ratio between stress and strain, and it applies within the regime where this ratio is a constant. In other words, there's a linear relationship between stress and strain. With shear stress and shear strain, the situation is kind of described in this picture right here. You have two forces applied to an object, but instead of being applied sort of like along a straight line end to end, one is applied a little bit higher than the other. In other words, they're offset by some amount that I've called h here, which could kind of be like the thickness of this slab of material here. There's also an area A, but the A that represents area here is not a cross-sectional area, but is actually an area of the top and bottom face, at least the way that this picture is oriented. I put over here in my whiteboard section that stress is equal to force divided by area, and I put two little vertical lines here, which to me that means parallel. In other words, it reminds me the area itself is kind of parallel to the direction of the force. So that's, I don't know, that notation may or may not make sense from a fully mathematical perspective, it turns out, but it kind of helps to remind me this is not a cross-sectional area. This is maybe, normally pressure is force per area is a little bit more like either Young's modulus, and we'll see it come up in bulk modulus. This is a little bit different because of the direction that the force is being applied. At the strain part of this, we have the ratio of delta x over h, and delta x kind of represents this shear deformation. So that's like a certain amount of deflection that's happened here for the top surface in this picture. I may be assuming the bottom surface was held stationary or something, although that doesn't necessarily have to be. But again, that deflected amount. There's also something called the shear angle, or you could say shear deformation angle. And in that sense, when you say this ratio of delta x over h, that relates to the tangent of phi, which is that angle. And I've drawn a little sketch down here of why that relation holds, because this angle is really representing the angle that is a result of this shear being applied. In other words, if normally this object would just be perfectly vertical, now the shear is applied and it's leaning to the right. The angle that describes how much it's leaning to the right really is that shear angle. And looking at this right triangle here in the picture on the right on the whiteboard, you can see that the opposite side of that angle is delta x, and the adjacent side in this triangle is equal to h, so hence tangent being opposite over adjacent would be equal to delta x over h.